to our regional transportation seminar. PacTrans organizes regional transportation seminar each quarter. We only invite distinguished practitioners and researchers come to share their stories. So this is our 2025 spring quarter regional transportation seminar. And it's our great honor to have Professor Michael Zhang from UC Davis come to deliver his talk. Actually, Michael has been in the transportation academia for a long time. Actually, when I was a student, I was aware of Michael's work. He does outstanding research work in system applications to transportation systems. So Michael has been the associate editor for Transportation Research Part B for many, many years, right? He's the longest serving associate editor. And Michael has also been a faculty member. His primary appointments with the civil and the environmental engineering at UC Davis. He's also an adjunct faculty member with many other departments, including computer science, public policy, etc. Michael is going to share with us his recent research playing the cat and the mouse game between traffic routing and signal control with 3 consoles, results and implementations. Transportation engineering is facing a lot of challenges, right? How do we balance the demand and the supply using technology, in the newer technology we have over the past years? So that's been our very important research topic. I'm very glad that Michael bring his new research coming to here, share his research story. Let's welcome Michael to start his seminar talk. Thank you.
Thank you, Yinghai, and I want to thank both Professor Wang and Professor Cynthia Chen for inviting and hosting me for the PAC Spring Quarter Seminar, and also Hida and Christine from the PacTrans staff for their support and make arrangements for my travel and so forth. Well, this work is not really brand new, and some are done like 10 or 15 years ago, and some are really brand new that we just came out last week, some of the results, and actually some of the results were done with Jeff's former student, my postdoc Ray Ma, and so there's a lot of connection between the work and the UW as well. Really, I would like to talk about is a topic that I have been interested for a long time, and I'll outline my talk. First is what motivated us to do this problem, and then we look at this from 3 levels: the long-term planning level, the intermediate term day-to-day operations, and then the short-term real-time traffic management perspective, and then I'll summarize the results. So before I came here, I took my maps for the traffic congestion level in the Seattle area. On the left, it's 11 a.m., and on the right is 4 p.m. So one is non-peak, and the other is peak travel. And then you see the color. The red is the highlight the congestion, and the yellow are moderate, and then green is no congestion. So the different time periods represent different demand levels, the different traffic load. So it's really whether you have congestion or not. The number 1 determinant is how much traffic demand you're going to have for the network, right? And then not only that, but you have the traffic demand, and then you want to go from, for my cases, from Seattle International Airport to University of Washington campus. And then I just look at this one is actually using the iPhone, Google, not Google Map, it's using the Apple map, because the Google map only give you the single route, the recommended, and the Apple one somehow give you 3 routes and tell you, the alternatives, of course, is also highlight the shortest routes. So when we have travel from A to B, and there's many choices of routes, also affects the traffic congestion level, because that puts the load on the road, on the intersections, on the interchanges, on the segment, and so forth. And in this particular case, I want to point out an interesting thing is that you can see that this route is 38 minutes, and that route is also 38 minutes. So those two routes have the same travel time, and these are longer routes. And in transportation systems, we have this concept called a user equilibrium. So what's the user equilibrium is that we believe, and it's also kind of empirically supported, that people will choose their shortest routes. People will choose the shortest travel time or distance, or we call it travel cost. But if everyone chooses the shortest path, if you use the same path, that path will be congested. And then initially, maybe this is like 20 minutes, and more people choose that, and become 25 and 30. And then, and if it's even more, it will become 35, and even more maybe become 40 minutes. Then some people will look at this app, and then I'll switch to this route. So there's this adjustment process going on based on the traveling information of the routes. Before the smartphone era, we just do this based on experience. Like today I tried this route, and tomorrow I try another route, and then it takes a longer time to settle down to this kind of equilibrium. But now with at your fingertip, it's this travel information and right guidance system, and then you can actually hopefully converge to the equilibrium even quicker. So how you choose the routes also affect the load at the intersections and the interchange and so forth. So that affects congestion. Okay, so this is a picture from an interchange in Israel, and that highlights the role that bottlenecks play in forms of congestion. So in this case, the bottlenecks are the intersection with traffic lights and interchange, and then if you have too many people routing through this interchange or intersection, the traffic load is very high, and then if your traffic control are not properly set, or even you properly set your traffic control, you just overwhelm that, and then you have long congestion, long queues, and in this case, you can see the traffic are backed up and even blocking the intersection. So the traffic control also affects that. So put this together, it's really a loop, a game between the routing and the traffic control, because how you choose your routes depends on how long what's the travel time, and what's the travel time depends on how much traffic are using these routes and intersections. So that feedback, and so you adjust your traffic control based on the demand, the load, and that is based on people's route choice. And then this load and traffic control determine the travel delay, and that feedback to your route choice, right? So this is a loop, and it's like a game. The traffic controller is a player, and the routing, will abstract the routing, although the routing is done by numerous people, but they're using the same principle, is try to minimize their own cost. So we can consider that as an agent, and that's like a game they play together. So there's interaction between them. So before, when we do the traffic control, normally we just disregard the routing. We consider the load is given, and even real time, we just measure it and say, so we're not considering the effects of routing. And oftentimes, when you do the routing, you just have a delay function. You're not really consider the actual control. So these are decoupled, and in practice, oftentimes. So the first people one of the first to recognize that is Mike Smith, a professor from the UK, and he looked at this joint control versus the routing, and you can look at this problem from multiple time windows. One is the long-term planning. So in that case, the routing is not real time. It's basically like we're doing the traffic assignment using the user equilibrium principle. And then the control is also not real time. It's basically allocated the grain time to the network. So you can look at this from the long-term point of view, or you can look at it from the intermediate term, which is the traffic evolve over time during a day. and from day to day, they reach kind of equilibrium. We call it dynamic user equilibrium. So Jeff Ban is an expert on that topic, and that's the work done with Ray Ma and a couple years ago. And so you can look at this day-to-day dynamics and the equilibrium. We call it dynamic user equilibrium. So that's the intermediate term. Now the traffic is not static. It changes over time during the day. And the third one is real time. It's people are, the traffic control adjusts the traffic lights based on the demand in real time. And also people reroute. So remember I showed you this route, so that's from the beginning to the end. But if I travel somewhere in the middle, and then I look at this, oh, the route's no longer, my original route is no longer the shortest path. Let's switch to another one. So this, en route, this rerouting, and that's real time. So you can look at from really adaptive routing and real time. So from these three levels, and we then work on these two levels. And I will just summarize the work done by Mike Smith on the first level, the planning level. I think the planning level is less useful in the sense that, for planning, mainly you're not really interested in the control itself, but more interested in the network throughput and performance and so forth. But in this and this level, you really want to make the control respond to traffic and taking into account the people's rerouting behavior. Okay. Yeah. So before I do that, I just want to use a simple example to show the highlight what we meant by this interaction. So see, I have two OD pairs, origin, destination, and just to make it simple, for this OD pair, I have two route choice, and here there's two traffic lights, and then your route choice will depend on how much traffic at these two intersections, and that will determine how the traffic lights works, and that will determine the delay, and that will affect the choice of the two routes. So that's the interaction, the loop, and if for these two paths, and in the static case, if their travel cost is the same, and if both are used the same, that's what we call a user equilibrium. And if it's a dynamic case, then if you depart at the same time, and then you have the same travel time, that's dynamic user equilibrium. So that's and then for the traffic lights, and this is a very typical four-way, four-stop intersection. And the traffic lights, typically you have the cycle length. That's one complete indication of the green and red and so forth. And then you have the movements are numbered by this NEMA convention. And here the right turns are ignored because they impose the least conflict. So it's just left and through. So you have 8 movement, and the different movement combinations you can form, we call a phase. And each phase will receive a dedicated grain time. So we call that grain splits sometimes, or grain time. And then for each movement, you have the flow. And also for the lag, you have the queue and delay, and also the grain time, and so forth. So that's the basic idea of the traffic control, is how to allocate these grain times for the phases. Of course, the cycle lengths can be subject to optimization as well, right? So how long the cycle lengths will be, and how many phases, and so forth. But most often, people will just look at with the given length of the cycle lengths and how to allocate the grain time to different phases. So I want to just quickly summarize the results for the long term, the planning. And Smith did a serious work and published papers in the 1970s and early 80s. He basically considered this planning problem with the static traffic assignment, user equilibrium assignment, and then have the traffic signal control allocate the flow, the capacity of the links. And he came up with this policy called P0 policy. So remember this, let's say this is phase I, and this is the queue length of phase I and the grain time of phase I. So for all the phases, they have to be equal. So that's called a P0 policy. So what does that mean physically? Physically means that if you have longer queues, I'll give you more grain time. That's it. Yeah. So for this intersection with all these phases, if this phase has a longer queue, I give you more grain time. And then he actually showed that this policy can minimize the total delay and maximize the network throughput. If you just have one OD pair, it's very easy to define the throughput is the max flow you can carry through the OD pair. But if it's multiple OD pairs, there's actually the throughput of a network is not clearly defined. So what he did is he applied a multiplier. You have a fixed OD demand and an OD flow, and then you time that with the scalar, and you maximize the scalar. That means the highest possible scalar means it defines the maximum throughput. And he showed that this simple policy that longer queue gets more grain time, then you maximize the network throughput and you minimize the total delay. So that's the result. And he analyzed the property of this model and so forth. Now let's focus more on the dynamic case. The first is the intermediate term control and routing. So in this case, we consider the people still minimize their own travel time by choosing the shortest routes. But now you have different departure time windows. Like you start at 8 and 8:15 and 8:30, and so this doesn't matter which time you depart, as long as the same OD pair and you depart at the same time, then your travel cost would be the same at the user equilibrium. But the thing is evolving over time. So again, the traffic control really is to allocate the grain time, and that will determine the discharging capacity. So when you have like intersection, let's say the northbound and southbound, and the control will allocate during 1 hour how much maximum number of traffic you can discharge for north and southbound. So that's the capacity. And then we have the objectives to have the traffic control to minimize the total travel cost. In here is mostly the travel time. This kind of problem is called a MPAC, mathematical programming with equilibrium constraints, because we have a minimization problem, but then in the constraints, it's a user equilibrium problem. It's an equilibrium problem. So that's, and then that problem is actually pretty hard to solve because normally it's non-convex, and then because the equilibrium constraint is nonlinear, and so in this case we use a path solver. So it's a solver in the software called GAMS. It's an optimization software package, and there's a particular one to solve the user equilibrium problem called a path solver, and we can only solve for local minimum, because for non-convex problems, we do not know how many minimum the problem has. And even we find one, we don't know whether it's a local or global minimum. I will not go into the details, but we need several components to do this. First, we need to model the traffic. So how to model the congestion, like the flow in, flow out, and the queue, and we're using a so-called double queue model. So for those of you who are familiar with the traffic flow, so the double queue model is really a representation of the Shockley model when the fundamental diagram, that means the flow versus density, is triangular. So if the diagram is triangular and this double queue model is exactly the same as the Lighthill-Whetham-Richard Shockley model, and that model is given by a PDE, it's hard to solve. But this model is given by ODE, so you just care about the queue in the end and the queue in the beginning. So, but they are identical when the we call the fundamental diagram is triangular. When it's not triangular, these two are not identical. Yeah. And then we have the signal control. We just allocate the grain time for for the phases, and then your capacity is the the original capacity and your share of grain time, right? For example, in 1 hour, your original capacity is, if you continuous grain time, is 2,000 vehicles per hour. But now you only have half of the grain time during the hour, and then your capacity will be 50%, and that would be 500 vehicles per hour. So this is the new number that we're going to model the capacity, and the control reflects the new capacity here. And then the user equilibrium is given by either a variational inequality or a nonlinear complementarity problem. So here is a so-called nonlinear complementarity problem. There's this function, travel cost. It's embedded in the user equilibrium, between the cost between the OD pair. So that relation is very convoluted. It's very hard to solve because it's an implicit function, and then we have to do some approximations to step by step to approximate this, and then forward moving the solution and so forth. So there are some of these details need to be worked out. And then we have all the constraints, including the initial condition. We start from an empty network, and we load the network over time. And the terminal conditions that by the end we clear the network. No cars will be left in the network. And then we have non-negativity for flow and queue and so forth. And then we know the demand for each time window, each time period. Yeah. So once we solve this fairly complex optimization problem with the equilibrium constraints, and we applied it to the very well-known Suix force network. So for those of you who work in traffic assignment, you see this figure. It doesn't matter it's lying down or standing up. You recognize this network, and then we have the OD demand. The OD pairs are given here, and these are the total demand, and then we release that over time windows, and these are the topology of the network, and these shaded nodes are with signalized control, and these are the origin destination nodes. So once we have this network and we use the path solver to solve the formulation I showed you a couple of slides ago. And then here's the results. I think for that network, we have 4 cases. And one is we use fixed time signal control. That means we determine the signal timing ahead of time. No optimization, just give the numbers to it. And we try our best to come up with reasonable numbers. And then we just use it. And that's this row. And the others, we apply our optimization. And that's this row, the adaptive control considering equilibrium constraint. The column, this is, we said, OK, the travelers will choose their shortest path. So they satisfy the user equilibrium. So we have the UE condition. This one is that we will allocate the flow to minimize the total cost. So that we call the system optimal dynamic traffic assignment. Basically, we assign the best path possible and of the flow, and so we minimize the total travel time. And that we not satisfy the user equilibrium condition, because for the same OD pair, different paths may have different travel costs in this case. So this is the results. Suppose we use the fixed time with UE constraints as the base. Okay. So if we're using the adaptive, the optimized control, we get 33% improvement of reduction. So that's this case. So this is the base. It's fixed time control with UE constraints, and this is the optimized control with UE constraints. So that's 33% improvement, reduction of the total travel time cost. And this is the case that we do not have user equilibrium constraints. And then we just compare the fixed time and the optimized solution. They are 37, 30, so they're very close. They're very close. So what does that tell us? That tells us that if you do optimal dynamic traffic assignment, you already almost reach optimality, and the signal control does not matter that much, whether you're using adaptive control or you're using fixed time control, because once you fix this, then I optimize around you. So the main effects is routing. So the routing has the most improvement, which actually is true from empirical evidence that even people try really, really hard to change the signal control. Oftentimes you see, oh, I have 5% improvement, I have 10% improvement, and 15% is very, very significant. So just changing, because the signal is already working very well, particularly like the adaptive vehicle actuator control, and the margin for improvement is not that much. But if you reroute traffic, and then there's a lot of room, because there's a lot of spare capacity sometimes, and you can do a lot of improvement by by doing the routing.
But because that's also changed the individual intersection demand.
Yes, that's exactly. You reallocate the demand, and even your intersection may be not very well timed, but you reduce the load to them, and you shift to some other routes, intersections. So the demand change give you the big bang of the buck. That means if you can do optimal routing, that's give you the best benefit in the existing network. And the other thing that user equilibrium actually, in a lot of cases, is a very negative effect. Although we think we try to minimize our travel cost, that should be good, right? But then it's a competitive game, because you want to minimize yours, and he want to minimize his, and she want to minimize hers. You don't have a goal to work together to minimize the total cost. You only minimize your own cost. So that if there's no congestion, you have very large capacity, that will give you the best results. There's no congestion, everybody takes a shorter path, and that's the best solution. And so the UE and system optimal is the same. And if you have really, really heavy congestion, there's nowhere to go. And then they also come fairly close. But in the middle, whether you do UE and system optimal, it makes a very big difference. So sometimes it's like LA, and the routing also doesn't really help that much, because it's just so congested. There's nowhere, no spare capacity to make good use of it. So the most improvement is in the middle that you can have. So that's the kind of the implications for this work. So now let's look at the short-term routing. We done two type of work, and this is the first part is done maybe I think 7 years ago, and so we look at using simulation and also using adaptive signal control and also hyperpath routing, stochastic routing, to see that if we do this in real time, what would be the results. So what we did is, for signal control, we look at 3 different control level, 3 different control. And so for low density means the light traffic, low demand, and then we'll just use the vehicle actuator control. So the vehicle actuator control is that you have sensors at the intersection upstream and measure the demand, and then if you have a very busy demand, then you keep on extending the grain time to that until you reach a max. Then you give the grain time to the competing directions. Or if your vehicle, you have a bunch of vehicles coming, but then there's a big gap, it's become less busy, and then you terminate and give it to the competing approach. So that's called a gap out. So basically, vehicle actuator control is really changing the grain time based on the demand. You either max out if it's very busy, or you gap out is if you're starting busy but then less busy. So that's the vehicle actuator control. And then when you have, we call it high density, is a higher demand, and then we have this, we call it a fair allocation of grain time. Basically, how much, this is a total grain time for for a cycle, and how much you got depends on your demand, share of demand. So you have high share of demand, it will give you more grain time. So that's very similar to the P0 policy. The P0 policy is dependent on the queue length, and this one is dependent on the demand, the flow rate. Yeah. And then my student implement the last one is called a phase selection. So he's doing a local optimization. So he used the sensor to get the demand, and they estimate if I give you grain time for this long, what would be the number of vehicles passing through this, this lag, and then you sum up to the total, and then he do a local minimization optimization to select whether to give how much grain time to that. So we call it a phase selection algorithm, and then we just implement. So there's this long formula. Just I don't remember. I don't remember what the details. But so this is basically minimizing the stochastic travel time. It's the hyperpath. So because we model each link the travel time as a random variable, and then we look at the stochastic shortest path. So this is really a formulation for the stochastic shortest path. So why we do the stochastic shortest path is because originally we just do a shortest path. We found out that because this is a dynamic situation, so sometimes people loop back. So you choose this path, and then you come back and you choose again, and it keep on looping. But once you random on the travel time, you avoid this looping phenomena. So that's part of the reason we use the this hyperpath approach, and that avoid this looping effect. But also, actual travel time is kind of random in a way. Yeah. So at that time, we just implement this in a 10x3 grid network with the Sumo. So Sumo is a traffic simulation software, microscopic simulation, so you can model the movement of vehicles. And so those are the details of the Sumo modeled intersections. And there are boundary intersections like a T, and then there's the four-way intersections. And so this is a simple network. And then we implement our hyperpath routing and also the 3 levels of control. So here's the results that we tested. And so the solid line, we call a with. So DTR is dynamic traffic routing. So the solid line is with dynamic traffic routing. The dashed line is without. So you can see that with is the also we have the network load. These are 500 vehicles in that network. The total number, will the demand, and these are 3,000, and then we'll load it. So we have different levels of congestion by different load levels. And one thing is that you can see that the travel time goes up, of course, if your load become heavier, right? So there's more and more congestion. But compare with the with and without routing and with routing, without routing, with routing, and so with routing is always have better, smaller travel time. So, and then there's different control algorithms. So the yellow is the fixed time, and the green is the low density. Is the green, that means the vehicle actuated, and this is the high density. Is the fair share of grain time, like similar to the P0 policy. And then this is the phase selection, phase optimization. So the phase selection has the best performance overall because we locally optimize the phase. But the fair share, like similar to the P0 policy, is also did pretty well. But because we're optimizing the signal, you see the gap between routing and non-routing is smaller. But if you're not really optimized locally, then the gap can be bigger. So that means if you're not really optimizing your signals, then with routing, you reallocate the load and you can get better benefits. Yeah. This is the percentage of non-routing vehicles. So that means 100% vehicles are without rerouting. So you just fix their routes. And this is 100% of vehicles have rerouting. You can reroute them during time. So this is 500 vehicles. It's kind of light traffic. And then the routing really, the percentage of routing doesn't make much difference. And when you have 6,000 vehicles, more congestion, then with routing, this 100% is typically better than without routing. But actually, 100% routing does not give you the best performance. It's somewhere in the middle. So that means if everybody is rerouting, it's not as good as like maybe 20% or 30% of the vehicles are rerouting. So that's not surprising because many previous studies actually also reveal that this route guidance is better to be done in the not 100% and with the like I think the results are more like a 30% or something like that is give you the best results. So these are kind of consistent, and also different controls. Again, the fit selection give you the lowest travel time, and the fixed control, of course, gives you the worst because it's not adapting to the traffic situations. So after the student done that work, and he was also at the same time doing a computer science master's degree. So he wants to, so that's like 7-8 years ago, and he wants to use reinforced learning to do this work. And I'm sort of doubtful because I told him that this neural networks is nothing new because I done that 30 years ago in my dissertation. I used back propagation. I said, but he wants to do a thesis, master's thesis on that. I said, oh, go ahead and then do it. So I said, I just give you half a year to do it. And if you cannot get that done, then we move on, okay? So he did half a year. It didn't converge. So it basically, the algorithm doesn't converge. So that's that, and we moved on. And now I have a new student, and she's all machine learning. So everything she's done will be machine learning. And she said, I want to do machine learning on this and that. I said, OK, no, try this. And to my surprise, actually, she, this is done just recently. She got quite good results. I don't know what's the trick. I don't, although I have the materials, but I don't know a lot about all this. So this is the part I will go very quickly. I go to the results because I don't know the details. But so basically, he has two kind of agents. So called a multi-agent deep reinforced learning, and so it has signal control agents. And then there's the routing agents. So the signal control agents control the traffic lights grain allocation. The routing agents, tells the route, which route you're going to choose. And then for the local control agent, so basically the waiting time, for each approach lane, and also how many vehicles are waiting and are approaching. So those are the state, and the reward will be the total waiting time and queue and number of stops and typical performance. And then for the routing agent, again you have the number of vehicles downstream, and so that will tell you how much reserve capacity you're going to have. And also vehicles arriving to this rerouting agent. And then the reward is how many vehicles have arrived to the destination. So you want to maximize that. So those are the states and reward. And then this agent, because you have the signal agent, this signal and your downstream signal, your upstream, your nearby signal, they are related. So you have to communicate with them. You share your information. And the routing agents and the signal agent, if my routing agent routing a path has this signal, and then they have to share information. So these are define the mapping between these agents and different agents. And then you, because you have to share information, so you concatenate their states together, and then you also using the weighted reward for the whole group. And then this is the policy that that you're going to come up. So for signal agent, we do the same for the routing agents, and then you use this as the architecture. So those agents have the state vector, and then you have the action that will give you the grain time and the routes. And then you come up with the performance will be the reward. And here she used called an actor critic. So for some of you who do machine learning, probably very familiar with this network called actor critic architecture, and to implement the approximation of the traffic. So this is the algorithm. Don't ask me questions about this, and I'm not I have to tell to ask her about the details. And then these are the feed forward and the long short memory architecture of the network. But I can tell you the results. So again, this is the Zwick false network, and we have. I thought I have the information about how many agents. Oh, yeah, here. Yeah, the 17 signal agents and 12 routing agents in this network we used, and this is the reward, the training episode, and then the kind of a convergence of the reward. So that's the training, and then for the results, this different color are different agents. And then you can see some are converge rather quick, and others are slower. But all of them tends to converge. And then these are the local. These are vehicle routing agents, and these are not as prominent because you can see this one is kind of did not really improve that much, and some are, most of them seems to be okay, but there's a big group and have improvement, but not as big. So that means these agents, depending on where you are, maybe play quite a different role. Some agents are, for example, some agents are on the, across like a Golden Gate Bridge or the Bay Bridge. This will have lots of traffic going out, and then maybe your routing has a larger impact and can make a bigger difference versus, a local street agents only affects a very few vehicles and things. So the agents are quite different performance than the signal control.
So these agents, So these agents are all place-based.
Yeah, they are like yeah. So it's not a vehicle based. It's at a location. Yeah, at a specific location.
All decentralized or?
They are decentralized, but they share information. Remember, there's neighboring signals, and they'll share information.
They only share with neighboring.
Yeah, the local.
agents.
Yeah.
So it's not a centralized.
No, it's not centralized.
Okay.
Yeah.
So I can understand the signal control agents are at the intersection that need to be controlled.
Yeah.
How about where are the routing agents?
The routing agents are basically you select the links, and then at a location you. So how to select the links? That's another issue. Yeah.
It's
So.
not studied here, right?
Yeah, it's not studied here. So she put agents in the place that she thinks will be good for the network. But what's good and how you place the agents, that will be another kind of dimension that you can look into. Yeah.
So there's 76 links. You only have 12
Yeah.
agents in there.
Yeah. So it's not because. Again, there's a dimensionality problem for the training, because if you have like 100-some agents, you could have a hard time to converge. So that's that's a problem.
12 routing agents
Yeah.
is also predetermined.
Yes.
by her.
Yes.
So there could be more or could be.
Yeah, it could be more and could be placed at different locations.
I
Yeah.
see.
Yeah. Those are all subject to experimentation and optimization. Yeah. So these are the training curve for, we tested 3 scenarios. So we use, remember we want to have the signal control consider vehicle routing and vehicle routing consider, so the joint, the vehicle routing and signal control. And then we only do signal control, so the routing is fixed. We only do routing with no signal control. So those are the reward. The joint control converge to the best reward, and then the only signal control is in the middle, and then the only vehicle routing is actually lower. And then for the travel time, it's the same. And this here is kind of contradict what I had in the previous dynamic one, because in dynamic one the routing contribute the most, right? But here the signal control actually perform better than the routing only. So signal only performs better than the routing only, and I think that's because in the other case, it's like we put an agent on each link, each vehicle, yeah, on each vehicle. But here we only put like 12 agents on the whole network with 60 some locations. We only choose 12. So it's a subset. So you can see there's, although the result, I think it's contradict but not contradict, because we can explain this contradiction. It's basically you just have fewer agents and they are not optimized location in placed, and therefore your room for improvement is also have limits. Yeah, and so it's not really contradicting to the results actually. Then we look at this.
So this is the case when what you're saying is essentially human drivers are not really making decisions on routing.
So the agents will tell the vehicle where to go. Yeah,
Right.
yeah,
More sort of like
yeah, yeah.
autonomous vehicle.
Yeah, well, you just assume they comply, like you give them recommendation,
Exactly.
and they follow your recommendation. Yeah, so it's 100% compliance. Yeah. So we look at the statistics, and so we look at the total number of vehicles arrived. So that's that's the throughput of the network, right? So more arrive during the time window, the better. The average delay, the average speed of the network, and also the average queue length. So I just put some reference numbers here for the throughput. So if we're using the vehicle routing only, which give the lowest performance, and we use that as a base, then the signal control has 8% improvement over the routing only, and the joint control and the routing has 15% improvement over the base. And if you look at the average speed, the improvement is much better. So for the signal only, you improve 22% over the routing only. And then if you have joint, it's 30% improvement over just the routing. So, but I would see that this routing is just a preliminary, and we only have a few number of routing agents, and we'll place them in may not be optimal position. So based from the DUE, the intermediate case, we think there's still a lot more room and for the routing, that the routing can do much better than just signal control. But I was glad that she actually make it converge. So is that reasonable results, because 7 years ago we just could not get it to converge.
Maybe he tried every vehicle at Egypt. That didn't work.
But then you get this dimensionality for training. It's just too much you actually may not converge because the huge size of the problem.
And also the machine learning algorithm has advanced so much.
Yeah, so things have changed. There's this new algorithms, and I mean, she's telling me because we were thinking of writing a paper on this. She said, "Oh, this method, actor critic, is so old. It's only like she tried it half a year ago, and it become." She said it's old. There's new method come up. So this field is just going so fast. So she want to use a new method, machine learning method, to redo this work. And but you can see there's a lot of room to improve, like how you select the routing agent, where to put them, how many you're going to have the routing agents. So these are all trade-offs that you can do. Yeah.
But also for reinforcement learning, is that you have to set a lot of parameters. Yeah. So for reinforcement learning, my understanding is that you have to set a huge number of, like a big number of parameters that actually hyperparameters,
yes.
right? And that actually have no physical meaning. And so, and given a specific set of combination of parameters, you could get different results. And so that's the hard part. That
yeah. So I'll comment on the generalizability of
right,
the machine learning. I think that's my big concern is how if you change a network, how transferable is the results, right?
And also yeah.
Yeah. So to summarize the results, when we do traffic signal control, and particularly in both the intermediate and short term, we cannot ignore the route choice, because now people really look at their phone and do the rerouting, right? So the traffic demand for the signal does change, and you need to capture that. And also we demonstrate in all the cases the joint control, the routing and the signal control, when you consider them together, they give you better performance. But this is a hard problem to solve. For the intermediate case, I think we worked 2 years to get the results. It's because it's just a very complicated optimization problem, and it's a non-convex problem. And also, the model itself, how detailed you need to, is the double Q model a good representation of the traffic, or you have to use simulation. If it's simulation, then the computational complexity will increase even more. And also the stability of this routing and control. So in the real-time control, we just like a one short game. We just go through once, like from 1 hour, you release from the beginning, and then by the end of the network is cleared. But this routing, people repeat day and day. If you repeat this many times, do you get a stable solution? Do you converge to something? We don't know. We haven't really studied that. And then, these are all looks good, but what after you put it in the real life network, do you get the similar results, or it's completely different? So we need to have validation. We need to have testing and so forth. For the machine learning, I think it looks promising, but I really want to take a look at the how generalizable and how transferable the results are. So if you have to train each specific network for a specific situation, then that's not very useful, because for the traditional optimization, once we come up with a method, we can apply to any network as long as you give me the inputs, right? But if you only train for this and work for this specific case with this hyperparameters, and if you apply to another network, you have to recalibrate and do the hyperparameters, then that's a very time-consuming, repetitive work. So that need to be looked into. But I think it's looks a promising approach. There are many new things on the horizon. I think this is really a good time to be a transportation in the transportation field. There's autonomous vehicles are they are already running in San Francisco and as a taxi service, and now they're expanding to LA and other cities. So with autonomous vehicle, you have a lot more control of the vehicle itself. Not only that, the vehicle can serve as a control agent. For example, you can deploy a bunch of autonomous vehicles like police cars. You're marked with the police sign, and then you pace traffic on the freeway, to determine how fast you drive during congestion, and you can smooth the traffic, and you can platoon them going through with very short headways like here, and so these are really platoon vehicles going through intersections, and you can reduce the delay, fuel use, and so forth. And those are the human, model human-driven vehicle, you can see a lot of the stop and go and queue here, but here, all the vehicles are going through. So you can actually, if it's, you have some designated lanes for autonomous vehicles, you can completely schedule them like a train system, right? But I think the challenge is for the mixed traffic. so we have human drivers and autonomous vehicles in the environment, and the human drivers may want to game the autonomous vehicles or vice versa, and then it will be a transition period that maybe actually will have a loss of capacity and even more safety problems, because this interaction can be, have a negative impact until people figure out how to cope with the autonomous vehicles and vice versa. So
also have bikes and people.
Yeah. So this, I think it's in, it's a sea of people, and I doubt autonomous vehicle can navigate through this, this kind of traffic situations. Yeah. So these are the work done over more than 10 years, and with here are some of the references for our own work and other people's work, including Mike Smith, who did the pioneering work on the joint control and pricing. And then here are the students that worked with me and colleagues from computer science and electrical engineering, Professor Chua and Professor Goso. We collaborate for many years. And then it's supported by different funding agencies like NSF and PacTrans. Yeah, with that, I'd be happy to answer questions.
Thank you very much, Michael, for this very interesting presentation. I think certainly we try out the older technology, algorithms, and also the machine learning. What I can assure you is machine learning will work much better.
Oh, okay.
Yeah. So, when I was a student at the computer science department, we compare like a computer network with transportation network. Everybody in my class consider, computer network was more complicated, but I told them human factor is so difficult to model, right? Transportation network is a lot more complicated, and hopefully they recognize that now. But certainly, this seminar today, we scheduled two portions. The first portion is Professor Zhang's presentation, and we have some time for questions. And the second hour is actually the in-class discussion, for the particular class, right? So I would open up for questions. Anybody have any questions? Maybe we can do this for 10 minutes, and then leave Professor Zhang with the class. Any questions?
Students mainly. Yeah. I think we already
The student with priority. Anybody want to raise a question? Professor Chen has asked too many. Maybe I can ask a question. So Michael, I think this is very interesting. So what are the assumptions? Because basically, if you know how many of the drivers are rerouting, where they reroute to, where's the good place they need to reroute, right? So even we assume user equilibrium, but actually it's very hard to observe the true user equilibrium. And system optimization is better, but people do not know where they drive will be better, right? So what are the assumptions, behind all these, models you presented?
Yeah, so for the first one, the planning and the intermediate term, for those ones, they are not really real-time routing. They're basically, after many trials, you get a pattern. So those are not for operational purposes. They are looking at the long-term, impact. Like if we have this kind of traffic signal, and then we, this will be likely the congestion level, the capacity, and so forth. But for the last two, and these are real-time routing, joint routing and control. And in that case, really, you can use the algorithm and put it into a Google map or put it into Apple, the map, and give you suggestions of the routes, and that will affect the routes. And the signal control would, if you have ways of collecting that information, you share the information, and then you can change the traffic signal to accommodate the traffic to move more efficiently. So for the latter, and there's an assumption that this routing information would be somehow be conveyed to the traffic signal control, and that means you have to collect the information in advance, to estimate the demand for the intersection and so forth. As for the planning and the day-to-day one, there's a very strong assumption is that people have to follow, everyone will minimize their cost, and they know what their minimum cost is. So that's the traditional user equilibrium assumption. So those are fairly strong assumptions, because in real life, we maybe get close to equilibrium, but I think the equilibrium is really an ideal concept. Actually, in my class, I ask students to explore some of the, the path, the routes between campus and a place in the city. And oftentimes they come very close, the travel time. It's like during the evening peak, like 21 minutes, 23 minutes, and 25 minutes, and so forth. So that some of the key routes have very similar travel times. And that's a sign of user equilibrium. So although it's an ideal sort of like assumption, actually in some cases, they are not too far away. Remember I showed you that the route recommendation, and some routes actually have different congestion levels, but they have the same travel time. That's their estimate of travel time in real life. Yeah.
That's great. Thank you. I think certainly transportation networks are very complicated, right? So mixed flow traffic, people's decisions may not be exactly following what you want them to do. Yeah. But certainly get the problem simplified so we can get started. That's wonderful. That's a very important first step. Any questions now from students? Yeah, go ahead.
My question is more from the idea of knowing that in urban setting we have a specified roadway capacity.
Yes.
And so with this idea of a specified roadway capacity, could you comment on, and apologies if this question is a bit too strong, but how much of this type of work is trying to squeeze more water out of a stone as opposed to other higher capacity vehicles like public transit and things like that can provide other types of mobility options?
That's a very good question. Here all this work are trying to really make better use of existing capacity. Yeah, so basically, the routing is you explore. There are some routes maybe have less vehicles and have spare capacity. You route the traffic that way, and that will spread the demand and not concentrate on a few highways and so forth. We always say that transportation congestion is demand greater than supply, and you have congestion. So here we'll try to balance that, but with a single mode, right? So the other way is to reduce the demand, vehicle demand, like you're using buses, transit, or you're using carpooling, shared ride and so forth, and that will reduce the demand. And you see when non-peak, like 11 a.m., there's virtually almost no congestion on the network because the demand is low. So if you can use public transit or shared rides to reduce the number of vehicles on the road, and that will, of course, give you much bigger potential improvement, right? For example, if everybody share a ride, then you reduce demand by half, and that's huge, right? This problem has many dimensions. Definitely look at the different transportation modes, and that will also address the problem. But unfortunately, in many cities, the public transportation, like buses, is just simply not competitive. Just the other day, I have a visiting scholar, and he's here for almost a year now, and he doesn't have a car. So his mobility is very limited, and finally he wanted to take a bus to go to Sacramento and look at the Capitol, and then go to some shopping south of Sacramento. So it took him 2 hours for just simply a drive, even in congestion, it's like 30, 45 minutes. But the bus took him 2 hours. I get the same sort of story for my postdoc. He used to live off, in a city like Folsom. It's a suburb of Sacramento, and come to campus. It took him 2 hours, and the drive would be like 40 minutes or less. Unfortunately, it's not a very competitive mode. Personally, I think the transit has to really rely in the future on autonomous mobility. That we don't need these huge buses. Only in busy corridors, like in downtown Seattle and some busy corridors, you need these high-capacity buses. But most of the places, we just need a shuttle van with 5 to 10 people capacity, but they have flexible routes, flexible time, on demand, and that almost door to door. That will change the public transit system. I think that's probably because it's very hard to change the urban form. I know that we want to do more infill projects and things, but look, like Sacramento, the downtown it's basically offices, and everybody live in the suburbs. So I normally people advocate for high density and change the urban form. I ask them this question: for an average American family, what is their biggest asset? It's not their car, right? What's their biggest asset? Well, student, you probably don't, you don't experience, but definitely for staff and faculty, if you work long enough, what's your biggest asset?
The land they live on.
The house, yeah, include the land, and then so in here, the house can cost like $1 million, $2 million, right? So they buy a car, either EV or a Tesla. It's like $20,000, $30,000 or $50,000. It's much easier to change the transportation than to move everybody into downtown Seattle.
But the problem, I see the problem, if we don't check that, I don't think the autonomous will solve the problem, because you could have a shuttle but with one person riding. Doesn't help. So the guy who is the Georgia Tech person is doing the shuttle study. Pascal. So the average occupancy is like one point something. Right?
1.2.
Oh, that's
So
yeah.
it doesn't help because
Doesn't
of
work
the
well.
land use. So you have all the autonomous shuttles running, but it's only one person on it, so it doesn't help solve anything.
Yeah, so I think that it has to be some public policy changes. So if you have sufficient good service, almost like a door to door and with much lower travel time, then maybe there's another president will tax the car like tariffs, 130% tax on a car, and then owning a private vehicle would be very expensive. And then the other thing that as I get older, and you can think like if you live in a suburb, for me living in Davis, it's not really a problem, but a suburb. And when you lose your driver license, you lose your mobility, right? And there are many seniors, baby boomers. There are many of them, and they really need this service. Otherwise, they have to move out their house, and then you go to the retirement community or something like that. So if with the autonomous vehicles, and then they can live in place. I don't know that's a good thing for youngsters or not, because then they don't sell their house and then you wait longer, right? Mm-hmm. But they can live in place with this, and there's no silver bullet. And right now these autonomous shuttles, because everybody family has like 2 or 3 cars, then that's not convenient enough. So you have to have a set of policies to support that, to make the ridership, higher. Like Europe, they tax the gas at a much higher rate, and Canada tax much higher rate. So we're taxing nowhere close to that, right? So it has to be a combination of policies to make that happen. It's just offering that service may not be enough. Yeah.
Thank you, Michael. Our webinar is scheduled for an hour. We're slightly over time. So I would like to stop the webinar portion now. Michael will be around for another hour, so you people can talk to him in person. And we have cafe and we have refreshments there. So feel free to help yourself. Let's give Michael a big round of applause for his talk. Thank you very much, Michael.